Okay, so yesterday what we saw was that we're looking for kinds of functions fn. So let's call them yadin. That's what we do. These should be healthy functions. Okay, so they should satisfy the condition. Write it this way. Then you see that it's this. Okay, this is what we're looking for. We said once we have this, then it's easy to define. Then it's easy to define the harmonic cocycles because we get okay, so the almost harmonic cocycles would be defined, just reminding you, by taking Cn of x to be x phi n check minus phi n check, and you have to normalize it so that this is 1.
I don't think we said check.
We did say check.
Okay. No,
We have to put effect.
we said Cn. I wrote the Fn. And that we defined Fn. And then, okay.
No, once we have once we have a sequence of this form, okay, we define this thing, and it's almost harmonic, and but the average of the norm stays bounded away from 0, so you get a non-trivial harmonic cocycle in the limit. Okay, these are of course uniformly Lipschitz.
But in the end, you get a different representation, right? Maybe a different representation.
What?
At the end, you say you get a cocycle. It's with respect to a different representation than the one you started from, right?
Yeah. That's
you don't care about the representation?
Well, I do care, but for the purposes of the things we're going to do, we just need an abstract representation.
Are there like...
In fact, at some point, we'll just say that we have a unitary action on some Hilbert space. We don't even know that it's L2, that it's... So, I mean, well, it is separable, so it's isomorphic to L2, but it's just a different representation. We're only going to use the fact that we have a harmonic cocycle.
Are there like specific cases where you can know the limit to representation?
This is a active research. This is a very interesting problem, because if I could understand things on the finitary level, then this would start giving me a handle understanding connecting. So these cocycles basically come from, remember what I said yesterday, up to problems. Okay, so let me as part of the answer to your question, and also as a reminder, remember that one option that we wanted to take was, up to normalizing something, we wanted to take f to be, or fn, the indicator of a Fellner set. Fellner sets, remember, these are just sequences so that their volume grows, but their boundary is small, in the sense that if you start uniformly in the set, you jump out with positive probability. Sorry, you jump, the probability you jump out at one step goes to 0, right? So the boundary is small. So you basically, when you start uniformly the set, you're landing inside the set, deeply inside the set. So it's hard to jump out, and it gets harder and harder. So this tends to 0. Okay. If you think about a simple random walk on a graph, in order to jump out in one step, you have to land on the boundary. And if the boundary is too small compared to the volume, then the probability of that is becoming small. Okay. That's a measure of the boundary size. And this, if we chose this and then defined, normalized properly and defined the phi ends, right? Then we would get, so what we saw was that if you plug in Fn here, this would satisfy the correct, this ratio would just be 1 over the uniform, starting uniformly in Fn and asking for the number of visits to Fn. And somehow if you can't jump out in one step, you know, for big enough sets, you can't jump out in any finite number of steps. So you can make that kind of go to infinity, and it tends to infinity. You have to prove that it's true, but it is true. And you see, for sub-exponential growth groups, we'll discuss that in the future, Fellner sets, balls are just Fellner sets. Okay? Because if balls were not a Fellner sequence, it would mean the boundary is roughly the size of the volume. And if you know that for every ball, then you get that the ball has to grow like an exponential. Okay? So basically you're taking the indicator of a ball. Okay? Oh, what was the phi n? The phi n was not f, but it was applying the green function to f. Up to the fact that the green function preserves L2, and that's a problem. But for a large enough dimension, and after Gromov, we understand the small dimensions. So I can throw that away if I want to understand really what's going on in most groups. And if I'm looking at this case, then I'm really talking about, you know, how many times, so what is this function at the point x? It's how many times you visit the ball, how long do you spend in the ball starting at x? Expectation. This has to do with growth, I mean, basically, somehow. So understanding things on a finitary level, if I could, instead of taking the limit here as n goes to infinity, I would just do the x, phi check minus phi check, write this thing, and this has to do with the green function. It really talks about, you know, the finitary things in the group. So this is a very interesting situation that I would really want to understand. I mean, I think there's a lot to explore here, and I still don't know how to do things without getting this abstract representation. If I could work on the finitary level, then it would be very good. Okay.
What do you mean on the finitary level?
Just instead of saying, just fixing a large enough n, taking you know, the co-boundary of this function, and doing everything on finite. Everything that I'm going to do it at the finite level, but I can't because it's almost harmonic. It's unharmonic. I mean, it doesn't work as clean as what's going on today. Okay. Now, the fact that G does not preserve L2, so this thing lives where this thing lives in L0. So this thing lives in finitely supported functions if we take a finite set, right? And we want this thing to live in L2, but it doesn't always happen. In fact, the fact that G takes L0 to L2 is called the bubble condition. I mentioned it yesterday. And this bubble condition is not always the case. You need a dimension, whatever that is, to be bigger than 4. So strictly bigger than 4 dimension. So if you don't have that, you don't have the bubble condition. So for any groups, for example, Z to the D for D less than or equal to 4, it doesn't work. And in order to get around this problem, okay, so what is?
Should we know a dimension of a group? Or?
No, I said whatever that is. Doesn't mean, for ZD, it's D, but otherwise, for Heisenberg, it's 4. Okay? The 4-dimensional subgroups, I basically told you all of them except finite index extension. So it's Z1, 2, 3, 4, Heisenberg. I think that's all of the 4-dimensional subgroups. Finite-dimensional subgroups.
So in order to make this thing for every dimension, we need to attack those groups, or
Yeah, but that's not a problem. I mean, because we can classify them using Gomov's theorem, then we would. I would be happy with a theorem that says something for dimension large. Okay, you can prove actually that if you have large enough polynomial growth, the dimension is large enough, whatever the dimension is. Okay, so you can think of polynomial growth with degree at bigger than 4, strictly bigger than 4. As soon as you have polynomial growth with degree strictly bigger than 4, then you have the bubble condition and everything is nice. Okay, and so you would be left with, if you didn't know Gromov's theorem and you could work at the finitary level, you would be left with a few cases to analyze, and maybe those you could analyze a different way. Okay, but what I want to say is that what is this thing? Remember, G is the sum of the powers of the transition matrix, right? So it's basically looking at this operator, right? And again, we said this does not necessarily converge, it doesn't necessarily live in L2, right? So what do we do with this? Well, we could, if we want, truncate it, right? So if you have an infinite sum and you don't know how to work with the infinite sum, if you truncate it, you definitely take a finite sum here, definitely doesn't live in L2, it lives in L0, right? Stays with, well, it depends on P, but P will definitely take an L0 function to, a power of P will take an L0 function to an L2 function, okay? So if you only take finitely many things here, you get an L2 function, okay? And so it doesn't explode. And so that's what we're going to do. We're going to truncate, okay? So this is the whole purpose of the next lemma, and you'll see it coming into the lemma.
Why P to the finite power of that maybe. It is in L2, but we'll see.
What?
Never mind.
P is a contraction on L2. So it takes L0, which is inside L2, to L2. Finitely many powers of P will also do that. Infinitely many powers is no longer an operator that necessarily does that. Green function is an example. Green function on Z explodes, right? It doesn't even take the delta function into undefined. Okay? I mean, you have to think about it, but yeah. Okay? So what you do is you truncate and then you normalize. I mean, so you divide by the number of powers that you're taking. Oh, you'll see in a second. Okay? So here's the lemma. Okay, let F, this is left, let F L2 of G be such that, first of all, I want the Laplacian of F norm to be at most 1/2. This is a technical assumption. It's not so difficult. I mean, if you multiply F by a constant, you get this, right? I mean, if it has a finite Laplacian, right? But let's assume that it's also of norm 1. This is also a technical assumption. Okay? I mean, one of them you can normalize and the other one gives you an assumption, but basically you want something with not too big a Laplacian compared to its norm, okay? This is
Can we control both?
No. Multiply by constant, this is homogeneous, so. Okay, you can control both freely, you have 1 degree of freedom. Okay, and you want that the limit, so this is the more restrictive condition, as you take k to infinity, of 1/k sum t goes from 0 to k minus 1 of p to the tf inner product with f. Okay, let's take not in L2, but let's take real valued. Okay, if we did complex, it would just make things more complex, more complicated, right? But take real valued, it's easier to work with. Okay, when it's real valued, this is a non-negative number. Everything is defined. So we take and it'll be enough for us because at the end of the day, we're going to do this with f's, which are indicators. Okay, or normalized indicators. So that's it. So they're real value. And the assumption is that this limit is 0. Okay, you see where truncated sum is coming up. Okay, I truncate the sum, normalized by k, and this thing somehow, so I have an operator for every k, and somehow these operators, inner product with the original thing, are getting, smaller and smaller, more orthogonal to the original thing. So, okay. Okay, so these are the assumptions. Then there exists some function in L2 of G, abstract, okay, such that the Laplacian of this phi divided by this thing, and I probably want a square here because I probably want this to be homogeneous. Okay, so this is the term that we're looking for over there to go to 0, right? This is less than or equal to 16 times the norm of the Laplacian of F.
then,
Yeah. But you say, I only assumed that this Laplacian was less than a half. I didn't say how small it is. So the smaller you make this, the smaller you make this ratio. Then, so what this lemma tells you is that you need to find normalized L2 functions with this condition, this truncated condition, such that their Laplacians are getting smaller and smaller, right? So it translates a question about Laplacians versus, so this is Laplacian versus norm, right? Because norm one and Laplacian getting smaller and smaller, to a question about Laplacian versus this double thing, this Dirichlet energy. Okay? So that's how we get this. And in fact, it's replacing this machinery. What it's doing is replacing this machinery. These functions, you take them, you normalize them. Okay, you normalize them. So you get norm one, okay? You prove that the normalized version satisfies this condition, right? And then you just check the Laplacian and you get that the Laplacian converges to zero. So you get the function, so you get the corresponding phi is also converged. This ratio also converges to zero. Okay? So let's prove this lemma. A few steps, and I don't want to get confused. So the first step is to define. So actually, what's going to happen is that this phi that we're going to find is going to be a certain sum of p powers of p acting on f, truncated sum as we would expect. So it's not the complete green function, but partial sum. So let's give it a name. Let's say phi k. We define this to be the sum up to k minus 1 of PTF. Okay, and this is always in L2. Okay, because P is a contraction. Yeah, maybe I should write down. Maybe I should write down the few things that you should verify for yourselves. Verify for yourselves that happen before we even define this. You should verify that PF for any function in L2, let's make it an H. Any H in L2, H and H prime in L2. PH, first of all, is less than or equal to H. Okay, this is very easy to verify. Okay, P is a contraction. Okay, that's one. Remember, what is P? P is the, there's some random walk in the background, symmetric adapted random walk. Okay. Second thing to verify is if P is self-adjoint. This comes from the fact that mu is symmetric. Okay, is self-adjoint operator. I think those are all the properties that I need. Okay, in fact, you could have done this with any contraction which is a self-adjoint contraction. Okay, I think I'm going to prove this theorem just with any self-adjoint. But we'll see if we get another property that I missed, then you have to point it out. Okay. So that's all. Okay, so then I define this truncated sum. Okay. And in fact, what we're going to have at the end of the day, phi, my actual phi for the theorem is going to be phi of 2 to the k for some k. I'm going to find some k, going to exist a k, such that phi is phi of 2 to the k works. Okay, so I need to prove that for big enough k, that this function will satisfy that inequality. Okay. This inequality amounts to upper bounding the Laplacian, right? And lower bounding the Dirichlet energy. That's what it surmounts. Okay, so step one is to upper bound the norm of the Laplacian. Okay, so Laplacian, so this is easy. So one Laplacian of phi k norm. Well, what is this? So this is I minus p times the sum. What do I get? I have I minus p times the sum of powers, right? This is just I minus p to the kth power on f. Right, do you agree? It's a telescopic sum. Okay? Then what? Well, this is bounded by what? This is bounded by right? By the triangle equality and the contraction property. I just use the contraction, right, for this. Okay, so one just tells me that I get a 2 times f. Oh, cool, you see? This Laplacian squared is going to be bounded, whatever I take, whatever k I take, going to be bounded by 4 times the 4. So one of the 16 4s in the 16 here is going to be just the 4 bounding the numerator, and now we need to lower bound the denominator. Okay, so this is step one. Step two was to do
Wait, didn't we assume that? What? Oh, okay, sorry, never mind.
okay.
Yeah.
Now, yeah. For step two, what I want to do is I want to understand the Dirichlet energy of pk with itself.
Is there any intuition, like you're saying, Dirichlet energy, but you haven't think about it.
What? It's the sum of the gradients squared, right? All the gradients and you sum their squares.
Okay.
And it's a form of energy. It's a Hamiltonian that comes up in certain systems. For example, in the Ising model, things like that, or Gaussian free field, depending on the a priori measure. So it's something that comes from physics, yes. Hamiltonian means energy. So
This, I believe you.
it's something for thermodynamics. So you know that thermodynamics is magic, right? It's the
I still.
if you read Harry Potter, then there's actual magic in the world. It's called thermodynamics, and thermodynamics is they have.
Oh, I think you can say that all this discrete analysis we did on networks and this stuff, you can in your book you call all these things in that's how it's called. It's
Yeah.
like electric networks.
It has an equivalent thing in your electric networks, but Dirichlet energy is something much more general. It comes from physics. So this form, which we can also call E of phi, whatever phi k in this case, right? This is an energy for functions, and it shows up in many physical models. In many physical models, especially in thermodynamics, this thing shows up. So, for example.
This energy is like a way of showing that some networks are transient. If you find the energy, is that energy or no?
If you find
No, I must be confused.
no, but remember what it is. Integration by parts. It's just the gradient with the gradient. It's just the norm squared of the gradient. So I mean, you could imagine that the gradient of a function. The gradient of a function is giving you an energy. Even in the continuous world, this has like, it shows up the integral. This is something that maybe you've seen.
But I believe it's.
Okay. I mean, you could imagine forces applying between like neighboring sites in something. And this is kind of, measuring, how much force there is between each individual pair of neighbors and summing them all up and giving you kind of the energy of the system.
Electric field is like if it's preserving, then it's the gradient of some potential, electric potential. And then when you take the magnitude, which is the norm squared, and you get the energy of the field.
Oh, it's a physics. You need physical intuition, but you need physical intuition not from balls rolling down hills, but rather from electrics. Things which are maybe less intuitive if you haven't seen them. Okay. I mean, that's just philosophy, so we can treat it as a definition. It's not, but there is probably something deep behind it because it comes up in so many different situations. So, first of all, what I wanted to say is that we can check what is this Dirichlet energy. So it's I minus P phi k. Remember what we said? What is I minus P phi k? You get a telescopic sum, so you get I minus pk, right? Acting on F with phi k. Right? This is just a usual thing, right? And now we can move the I minus pk to the other side because P is self-adjoint, right? So what we get is that this
Also I is.
right? But this is another telescopic sum, right? This just tells me take a power minus that power plus k, right? So what are you left with here? You're left with the sum of F inner product with right, you remove, so this acting on phi k is the sum of all the powers up to k minus 1, from 0 to k minus 1, and you remove all the powers from k up to 2k minus 1. Sorry, you
Here we can write it and then.
this is F, you have the sum from 0 to k minus 1, minus the sum, when I do a pk here, I get the sum from k to k minus 1. Right? I mean, I just had all the powers,
Not from.
I had all the powers,
Okay, yeah.
look, I had all the powers from 0 to k minus 1, and I added k to each one of those powers, so it's from k to 2k minus 1. But now you see, I don't like this from k to 2k minus 1, I like 0 from 2k minus 1. So if I add all the powers from 0 to k minus 1, then I get 2 of these. Right? And add them back. Same thing. But then this is just 2 phi k minus phi of 2k. Okay? What I got is that this Dirichlet energy equal to, miraculously, you see just some magic happening here. I can complex conjugate because again, everything is real valued. So this is equal to yeah, I mean, this is already, this inner product with this is already 2 phi, right? So we get, this is equal to phi wait, what did I define phi k? Phi k is just the sum. So yeah, so phi k is 2 phi k with f minus phi 2k with f. Okay? So now I'm going to define a new object. I'm going to define a new object. This was one important inequality. Inequality. Second important thing is going to define, so 2, going to define AK. This might be a bit confusing. AK is going to be the inner product of phi 2 to the k with f. Remember, this is the guy I want to find It's good for me, okay? Some power of 2. So A does powers of 2 and inner products with F. And the equation we actually got here, right, was that the Laplacian phi of 2k with itself, which is, remember, this is what we want to lower bound. This is what we want to lower bound. We already have the upper bound, right? This is equal to, what does this say? This is 2 of AK minus phi 2k is 2 times 2 to the k is 2 to the k plus 1, so it's AK plus 1. So you see why the natural indexation is coming with the powers of 2. Okay, that's why we did this. Okay, so now we have this. That's the second one I want you to remember. Okay, third step. Third step is to now choose the proper K, or we'll call it M. Because we're using K as the index. Okay, so choosing the proper K, let's choose the proper K. So remember, we assume technically that I'm not going to have enough room on the board. We technically assume that the Laplacian of F has, remember, we assume that the Laplacian of F is less than or equal to half. So now we choose M. M is going to be special, such that it's the nearest power of 2 for this thing, right? So I want the following to happen. When the Laplacian of F, this is some power of 2. I want it to be smaller or equal to 2 to the minus m, but bigger or equal than 2 to the minus m minus 1. So m is at least 1. Okay? We can do that, right? Because if this is bigger than a quarter, then yeah, so what probably I want a strict inequality. I mean, to make it uniquely defined. I mean, this is enough. Find some m, it could be not unique, but this is what I wanted. Not what I wanted. What I wrote is different. Okay, what I wrote to in my notes is that I choose an integer at least 1, such that this happens. Let's see why this is good. I don't want to confuse myself. This is less than or equal to the m, bigger or equal than 2 to the m minus 1. And I can make it, strict inequality on one side if you want a unique m. Does this work? This we know is a number which is less than or equal to 1. 1 over any number less than or equal to 1 fits between some powers of 2, right? So this is, so this could be 1 if m is equal to 1, right? So if this was exactly a half, this one, so this would be 1 and m would be equal to 1. But the smaller this gets, the bigger m has to be.
If you make the inverse of this, you get the norm of the Laplacian of f between 1 over 2 to the m, in this side, 1 over 2 to the m plus 1.
Yeah, so what I wrote before was wrong. I wrote it impossible. It was impossible. Yeah, so here it was m plus 1. So that's, okay, good. Now we're fine. Okay, so this is the same condition. Okay, so I want you to remember that this is my choice of m. Okay? It's no choice. It's just the closest power of 2 to this number, right? So this is the second, this is, let's say, 3. So maybe this is not 3, but we'll say something about 3 in a second. Well, this is part of 3. I'll add another 3. I just want you to notice that we have something very, very cool. When we take this m, so notice that what happens when I sum all the k from m to infinity of 2 to the minus So what do I want to do? I want to do 2 to the m minus k, I guess minus 1, right? What is this? What is this sum? Should know this sum. It's a geometric. So what does it sum to? 1/2 plus 1/4 plus 1/8 plus,
You can
right?
take the 2 to the power of m, to the power of
It's
n.
1, right? So it's a probability measure on case, right? So now let's look at this probability measure is going to be an average for us for something. What happens when I sum what happens when I sum this probability measure? I take an average of 2ak minus ak plus 1 divided by, using this probability measure. Okay, so maybe multiplied by,
maybe
right? So I'm averaging these numbers,
expectation of something.
right? So it's expectation of something, okay? But what is it? What does it come out to be? It comes out to be, let's compute this, okay? 2 to the m has nothing to do with this thing, right? So it comes out. Okay, then we have sum, k goes from m to infinity, of 2 times
But this is a
minus k
probability.
minus 1, so 2 minus k ak, minus 2 minus k plus 1 ak plus 1. Right? So we just have this telescopic sum. We have to be careful about telescopic sums. We want the tail to go to 0, right? So if I sum finitely many of these, right? If I start a partial sum, then I need the tail of this to go to 0 for it to converge. So why does the tail go to 0?
Or you're asking us.
I'm asking you why this is true. I erased
The
it.
assumption.
The assumption, what is this thing? Let's parse this. Let's parse this. What does this say? This says summing, this says phi 2 to the k, that's the sum of all the powers up to 2 to the k acting on f,
And one over-
right? And 1 over the number of powers. That is exactly the assumption. The assumption that 1 over k sum. This is exactly the assumption, just applied to powers of k, powers of 2. Okay? So if I have this condition, then I know what these telescopic sums become. What do they become? They become exactly the first guy. Who is the first guy? So I have here, look, 2 to the m, right? Times 2 to the minus m am. Amazing.
But,
Miracle.
no, we have a miracle, but this, like we don't know why we choose that M.
We'll see, because it works, but okay.
No,
But
but
now, this was true for every m.
yeah,
This
that's
was true for any m. We'll see where we choose the m. But what I have is that this average, right? This is an average of some quantities. Okay, some real quantities which convert with the average converges and is equal to am. If the average is equal to am, this means that there is at least one of them which is at least am, right? It can't be that they're all smaller than am. Okay, so the consequence of this average computation was that, and this is what I want for 3. Together with the definition of what am is, there exists some k, which is going to be important for us. This is the k that we're going to use. Okay, let's call it, okay. So there exists some j, which is at least m, So because this sum is over the k's, which are at least m, right? Such that the guys being averaged upon 2aj minus aj plus 1 is at least am. You agree? Who I wanted most? Oh, one at least, okay. But what is this thing? This is this. Okay. Right, so I have a lower bound on the Dirichlet energy, which is what I'm looking for. Now we just have to understand what this lower bound gives us. Okay, so the fourth step is the lower bound am. This is where we're going to use the specific m. Okay,
Why is this true?
what?
Why is this true?
This? Because if the average of all of these for j greater or equal than m is equal to am, so there's one which is at least the average. We could have said if there's one, also there is at most the average. We want the lower bound. Okay, so this gives us a lower bound of the Dirichlet energy. So now we're left with lower bounding am. This is what we're going to try to do. For the specific choice of m. Okay, so okay, let's compute. M sum 0 to 2 to the m minus 1. Right? What am is. Okay? I claim that each one of these guys, so I'm doing t by t inequality. I claim that this is bigger than 1 minus t times t times the Laplacian of f, which could be negative, but still lower bound. Okay, so I need to explain why this is true. This is true t by t. Okay, but now when you compute this, okay, then you have two sums. One is summing over 2 to the m objects, you just get a 2 to the m. Okay, let me write this, so am, at least, this I want a blue one. So you get, if I explain this guy, right, which I haven't explained, but you will get the conclusion, which is 4, is that am is at least what? There are 2 to the m guys here, and then I'm summing t from 0 to 2 to the m minus 1, right? What is the sum from 2 to the m, right? It's this plus this times the number of summons divided by 2, which is at most, so it's 2 to the m, 2 to the m summons divided by 2 is 2 to the m minus 1 times 2 to the m minus 1, and I can forget the minus 1 is an upper bound because I am lower bounding, so minus like an upper bound. Okay, so at the end of the day, I get 2 to the m minus 2 to the m minus 1 times 2 to the m times Laplacian f. Read?
Not divide by 2?
Divided by 2, this is the number of summons divided by 2.
Oh, the number of summons.
And this is the 2 to the m minus 1, but I forgot the minus 1. Upper bound by minus. I mean, okay, strictly, I'd have to put a 2 to the m minus 2. So the correct thing to write here, so this is 2 to the m divided by 2, and this is 2 to the m minus 1. That's what I would have to have, right? But you can see that this is upper bounded by this. Minus sign gives you a lower bound. So this is what I want. We'll see how we use that in a second. Okay, but why is this justified? We need to justify this inequality for every t. Okay, we need to justify this inequality for every t. And well, this is basically just a Cauchy-Schwarz. Okay, so this is just a Cauchy-Schwarz. So let's justify it. So what do I want to? Yeah, I want to do one. So I'm trying to show that this is at most this, but it's enough to show that this is at most t Laplacian of f, right? Same thing. Okay, so I'm upper bounding 1 minus ptf. This is what? This is I minus pt. So this is just black magic. Okay, I minus ptf. You see something like this, you Cauchy-Schwarz. Okay.
So it's because the norm of f is 1.
Yes, yes. So you Cauchy-Schwarz, what do you get? You get I minus pt f norm times norm of f, which is 1. Okay? I minus pt f you write as a telescopic sum. Okay?
The square? No, you don't.
Okay? What is this telescopic sum? This you can take a pk out and put a Laplacian. The pk is a contraction. I bound the sum by the sum of the norms, right? Triangle inequality. So this is bounded by the sum of t guys of the norm of pk Laplacian f. But pk is a contraction, so it doesn't do anything, right? I can bound it by just by the norm, and then I just have at most t times Laplacian of f, which is the bound I wanted. Okay. We've done all the steps we need, and all we want to understand is what is this lower bound that we have here. And then we've completed the argument. Okay, so let's understand what this lower bound says. So in conclusion, erase this. And all the steps together. This. This. Okay, so phi is this guy. Phi of 2 to the j. Okay. Choose this for that special j. Okay. And now we want to upper bound this thing, right? So first of all, by 1, the numerator is bounded by 4. Right? It's bounded by 2, so the square is bounded by 4. Okay? By 3, this is bounded by a m. Right? By 2 and 3. So 2, it's equal to this, and by 3, it's lower bounded by, for this specific j, it's lower bounded by m. So this is 2 plus 3. Right? By 4, I have an upper bound, because I have a lower bound on the denominator, of 2 to the m times 1 minus 2 to the m minus 1 Laplacian of f. Just rewrote it. But remember, what was the choice of m? What was the choice of m? The choice of m was that I can I can lower bound 2 to the m, and I can upper bound 2 to the m minus 1. So I just put them in here. It's in the right direction. I want to lower bound 2 to the m, and then I want to upper bound 2 to the m minus 1, right? So this is bounded by, it's by the definition, so 3 This is upper bounded by, so I have a 4. I have the lower bound on 2 to the m is 1 over 2 Laplacian f. This is the lower bound on 2 to the m. The upper bound on 2 to the m minus 1 is again the same thing. So I have this 1 minus 1 over 2 Laplacian f, and this is times Laplacian f. These two cancel. I get a half, becomes a 4. 4 goes upstairs to 16, and I get, okay, so this is less than or equal to 16 f, which is what I wanted. Okay, so this is how you get around. This is the idea by Lee and Peres of how to get around. Truncating the green function to get around the problem with the green function converging. Okay, we take a break and then we'll see how these things tie together. Include the distance of the harmonic cocycle. So now I want to show you how to actually get these functions, right? So the goal now changed. We had the goal of getting this ratio with the Dirichlet energy to go to 0. And now this lemma showed us that the goal is now find Fn to norm 1 and Laplacian going to 0. Right? This is what we want to find. These are almost harmonic L2 functions. It's very nice because you start with almost harmonic L2 functions, you do a roundabout tour and you get almost harmonic cocycles.
What we did up to now is sort of translate the condition that we're looking for in different ways.
Yeah.
So it will be easier.
Yeah. Now, remember that there's one more condition we need to verify, and that is that the sum of powers, right? This was a technical condition that came up inside the proof. This had to converge to 0. So Cesaro mean of these powers had to converge to 0 for every n. Okay, so I mean we need it separately for every n. For every n, we get a function, then right. So for every n, this as k goes to infinity converges to 0. Okay, so we have to verify that thing. I just want you to notice that I can put in so that was the condition that came up naturally during the proof, right? Because we had at some point the telescopic sum, and we needed the telescopic sum just to be the first element. And so if you want a telescopic sum to be the first element, you need the elements to go to 0. In order for this to work, so this will follow if for every n, you write pt fn, and take t to infinity, you get 0, right? So this is a sufficient condition, not a necessary condition, right? Of course, sequences that go to 0, their Cesaro means go to 0, but not the other way around. Okay? So, so in fact, this is the condition that we will verify. Okay? We're going to find functions fn for each n, they're going to have norm 1. Their Laplacians are going to become getting smaller and smaller, and for each fixed one, when I take t to infinity, this thing is going to converge to 0. So construction. Now, of course, we want to use the fact that G is amenable. Okay, but first fix some finite set in G. Not going to do anything. And let's look at F, which is indicator of F. Now I want this to be in L2. This is in L2 if it's finite, it's in L0, right? And I want it to be of norm 1. I'm going to normalize so that it's in a norm 1 function, right? So this is the indicator divided by square root the size of F. And so F automatically has norm 1. This is easy.
Because the measure is the counting measure.
Okay. Next thing I want to do is I want to, okay, now maybe the next thing I want to do is I want to understand this condition, ETFF, okay? Now, what I'm going to say is that, so this is an exercise for any infinite irreducible, remember means connected, Markov chain. Okay. P, so P is a transition matrix of a irreducible transition matrix. P to the T xy converges to 0 for any xy, and you take T to infinity. Okay? Not a very easy exercise, but it is doable. Maybe I break it down into some steps. Give it to you. But since I don't want to lose the current discussion we're at in the Hilbert space and the groups acting on them, I don't want to go back to
Fix an x, for example, so this is easy, right? For fixed x.
right?
Then you know that the sum of PTXY, where x is fixed, sum converges to 1, right? General.
Y is not going to infinity. P is going to infinity. X and Y are fixed.
Yes.
It's sufficient to prove this for X equals Y. Think of why that.
Because PTXY is less or equal than PTXX, PT.
It's greater or equal, but you can bound them on both sides by some constants, right? So, but that's the irreducible part. But okay, if you think about this exercise, you have to use the fact that it's infinite. Not true for finite state spaces.
Even if it's recurrent?
Yes, even if it's recurrent. If it's transient, it's easy. If it's transient, the green function converges. Summing this over T converges. Definitely, this as a sequence in T, this goes to infinity, to 0.
Transient.
Actually, the transient case is the problematic case. The recurrent case is the problematic.
Yeah, because recurrent, it sounds like when something is recurrent, you think maybe the probabilities are bounded from below.
Yeah, but they're not. If it's infinite and irreducible, so you can get to any place, can't have too much probability accumulating at a point.
Oh, because it's irreducible.
Because you can get far enough away, so it's impossible to. But you have to think of how to prove this. This is not completely trivial. Okay? You need to think about the fact that for larger and larger T, you have more and more places it's possible to be at. Okay, so it cannot be that any one place kind of has. Okay? You should try to think of the lazy version first. Try to think of a lazy version of P first.
But it can go to infinity like slow, right? Because you have recurrent Markov chain.
For general Markov chains, it can go to infinity, to 0 as slow as you like.
Because the green function may diverge, right?
Yeah. But for networks, there is an upper bound on this, which is of order 1 over square root T.
It still may diverge, but it's not.
Yeah. But it can't go as slow as you like for networks. Networks, well, the constant of the square root T has to do with the conductances, the total conductance between X and Y. So if you have like the ratio of conductances can be different, but for fixed X and Y, this cannot go to zero as t goes to infinity as fast as as slow as you want. It has to go at least as like 1 over square root t for networks. But that's a special type of Markov chain. Here I'm just saying irreducible infinite Markov chain.
What depends in networks that is different in that sense?
They are special. We need to, it's electrical network theory. Okay. And that's completely non-trivial. The fact that a network has dimension, at least an infinite network has dimension at least 1, gives you a bound on the heat kernel. This is called the heat kernel. I hope I said enough sophisticated words to explain to you that this is something deeper than just saying it's on one.
I will focus on that.
On one foot. It's a very interesting thing. It's in the book. You can look at it. It's not it's not difficult. It's elementary, but it's I need to build the theory in order to explain why that's. Okay. But you can create general Markov chains for which this heat kernel, this is called the heat kernel, this sequence, okay, decays in t as slow as you like.
This feels really weird, right? Because for every t you get a generalized stochastic matrix, right? So but it doesn't have to, like in the finite case, you can't have this because every power has an eigenvalue.
What you need to think about is irreducible and infinite. As you're raising t, the probability measure is spreading out on larger and larger sets. Think of lazy. So these sets are strictly growing, right? Because if you could be at time t in a certain set, then definitely you could be there at time t plus 1. Just stay put for one step, right? So the distribution is spreading over a set and eventually becoming infinite. You cannot keep a point, bounded away from 0 in such a situation.
Then you would have,
Well,
the sum would be.
I mean, you could describe a key sequence of probability measures where 0, the origin has probability half, but this won't work in random walks.
Right?
You need to think of why the Markov chain rules this out. The probability measure is spreading out and it's in Markovian way, so they have to do with each other. It's not just a sequence of probability measures. So somehow you cannot keep, one point with large enough probability measure. In fact, again, as I said, first you make a reduction, you reduce to the situation where it's PTXX, and in fact, you reduce to the situation where P is lazy, where P has at least probability half to not do anything. Okay, and then you look at the lazy part and the what's called the diagonal heat kernel, the X is equal to Y. Okay, and then you prove it for that. Okay, so that's the hard part. So prove it for X equals to Y in the lazy version of P. The reductions are maybe you need to think, but they're standard. So we have this. So what does this exercise give you? Why did I bring it up? Well, I brought it up because we have the following situation. We want the condition, right? We want something to go to 0. It's going to come from this condition. So we have my finite Fellner set, okay? And we want to look at PT of FF. Right? What is this? Well, first of all, this is 1 over F. Where does this 1 over F come from? 1 over F comes from the normalization. Okay, I have 2 F's. It comes out squared. Okay? And then I have, what is PTFF? It's the sum over all X and all Y. So this X is going to be the sum for the inner product, and the Y is going to be the sum for this function, for the PTF, right? So I want PTF at X, right? So PTF at X is just sum over Y, PT XY, F of Y. This is PT, this with the sum of Y is PTFX, and then I have to multiply that by the complex conjugate of F, X, but that's just, okay?
So it's not exactly F, but the indicator, because.
Yes, the indicator, thank you. Now it's the indicator because I already took out the normalization. Good. What does this say? This says just start. See, the X's are restricted to start in F, and you start uniformly in F. And the Y's are restricted to be in F. So this thing just says start uniformly in F, and ask for the probability at time t to be inside F. That's what it says. Okay, this is what it says. And this goes to 0 as t goes to infinity. Why? Well, let's go back to this representation.
This is just a finite sum.
Yes, that's the reason. So
The thing goes to infinity.
I have this, right? And then I have this, and then I write this. So this is the same thing, but I just wanted to show you the probabilistic representation of it. For me, that's what I understand goes to 0. Okay? Start uniformly, I start from some measure, and I want to stay in some set, and I'm taking time to infinity. Just like one point, a finite set will also decay to 0 because it's impossible to keep large measure at certain points, so you can't keep it on finite sets either. But again, all of these go to 0, right? And it's a finite sum of such guys. So this goes to 0 by the exercise. As what? As t goes to infinity, fixed f, right? So the x and y's for each one, there's a rate that goes to 0. I have finitely many, so the whole thing goes to 0. If I had infinitely many, this would not necessarily go to 0. So this goes to 0, this goes to 0. Okay, this is by the exercise. Okay, so we verified the condition. Verify this condition for a fixed f.
Can I ask generally, because I thought about this question in other area, that if you start with a single point, the probability of landing at time t at a finite set as t goes, it's 0.
Consequence of that.
Might,
In an infinite connected chain, that's what's very important.
I might use it.
Basic.
I do basic things.
No, I'm just saying, that's not what you're going to make.
But
If you weren't aware of it, I'm happy that you're now aware. Okay, but prove it. Don't.
But it's not true for, I mean, if you would take general f, not indicator of a finite set, then it wouldn't necessarily go to 0,
F in L2.
for example.
I
I mean, if you, for example, if you knew that not just
so F
PT
in, so if F was just a finitely supported L2 function, a finitely supported function, then it would go to 0, right? Because what would be written here? Sum over all x and y, f of x, f of y. Now these all go to 0 and you have finitely many of them. Now I'm saying, okay, approximate L2 by finitely supported functions. I think that tells you that it also goes to 0. No? I think for L2 functions, this always goes to 0. For a connected chain. I need to think. Now I'm worried.
I mean, if you knew that the operator norms of PT are bounded, not bounded, going to 0, then it would follow by Cauchy-Schwarz.
No, but the operator norm is not going to 0. Operator norm is 1.
Oh,
In a typical, in a amenable case, the operator norm is 1. This is case 10 design. Yeah, so for finitely supported function, it definitely goes to 0. Okay, I mean, it's the same proof. For infinitely supported functions, for L2 functions, I need to think if you can approximate it in the correct way. But it might be true for infinite. Okay, what was the third condition we needed? The third condition we needed was the Laplacian, right? So now we have to compute the Laplacian of f norm. Maybe easier to compute norm squared, right? We want this to become smaller and smaller as we take f, set f bigger and bigger, right? At the end of the day, that's what we're going to do. And notice that until this point, we did not use amenable at all. We just used a general finite set in a group.
And then
We use the amenable, we'll take the following sheet.
What? Yeah, but we didn't use the fact that f had small boundary for any computation here. Okay, f was a fixed set. We didn't take f to infinity. We need something, amenability will come up in this computation. Only in the Laplacian computation where amenability comes up. Okay, so we compute the Laplacian. Good. So how do we compute the Laplacian of f? So what is this? This is the sum over all x of this function evaluated at x norm absolute value squared, right? But how do we write
You only care about x in f, right? Because otherwise it would be.
only care about no wait it's Laplacian of f.
It's the sum of the f of x.
I don't know how Laplacian of f maybe spreads things out. To be careful. Measure, I didn't say the measure was finitely supported, the random walk measure was finitely supported. So there's an average in there going somewhere, right? And maybe it's all over the group, right? So I have the sum over x of this at x squared. What does that mean at x squared? It means sum over y inside the square, right? Inside the square, sum over y of, what do I want? I want Laplacian xy, right? F of y, all of this squared.
What's Laplacian of xy?
Laplacian is just I.
Laplacian is I minus p.
Okay.
It's this matrix acting on this function. This is the Laplacian of f at the point x, this whole sum, put it squared, take the sum over x's. Okay, now let's see what this says. When I do the I, what is I of xy? The matrix I of xy is just y equals to x, right? So a different way to write this would be the following: sum over x, sum over y, pxy, which is a probability measure, right? And then do here f of x, which is just I acting on, because this sum doesn't do anything to, because this doesn't have a y in it, minus f of y. All of that square. The square is outside the sum, right? This is the same thing. Because this first sum just gives me f of x, that's if, minus pf. Okay?
I can pull out the p and
Now I'm upper bounding, remember? So there's no t here. No t. This is just fixed Laplacian one step, right? Why can I bring the square inside? Sum over xy, p y, f of x minus f of y squared. Why was this closure? I had a square outside the sum, I put the square inside the sum. But I didn't put it inside the sum, I didn't square the,
you just pull out the p, didn't you? Or
what t?
the p.
Yeah, but
No, it
Why?
didn't pull it.
I didn't get pxy
I want to
squared.
take Cauchy-Schwarz.
Ah.
It's true in a sense, but it's more basic than that. What is this?
And it's triangle inequality.
Fixed x, no. Fixed, square is not triangle inequality. Square is not a minimum.
Oh.
Fixed x. X is fixed inside the square, right? What is this? It's an average. This is an average. Square of the average is less than the average of the square. Jensen. Okay? Square of the average is less than the average of the square. That's why the p doesn't get squared. Now you could prove the square case using Cauchy-Schwarz. That is true. You split the p up into, I think if you split this p up into square root p, right? Square root p, then you get 1 on one of them, and the other one becomes right. So this version of Jensen follows from Cauchy-Schwarz. In fact, they're equivalent.
Because x squared is convex.
Yeah, I mean, whatever it needs to be for. Square of the average is less than the average of the square. Variance is non-negative. That's another way to say it. Okay. Okay. So this is the sum we get. Anybody remember what this sum is?
Divergence, the other thing.
Right. This is twice the differential energy, right? But okay. Okay. I'm not going to use. I want to show that this goes to 0, right? So I need to actually compute something. Okay. But let's remember what is f. What is f? F is up to the normalization, it's the indicator. What's going on here? This difference in absolute value, even squared, what does it say? It says 1 if x is in F, normal, I mean, after the normalization constant. It says 1 if x is in the set F and y is not, or if y is in the set F and x is not. So it's a symmetric difference. Okay?
Now comes the Fourier sequence.
Okay?
Metric difference.
And the symmetric difference between F, okay, so, sorry. It's the, not symmetric, yeah, it's the indicator that X is in the set, Y is not, right? Plus the indicator that, or bounded by that, the indicator that Y is in and not, but those are symmetric, and P is symmetric because mu is symmetric. So I can just bound this by 2 times the sum over X is in the set, Y is not, right? Because the other sum would be just Y is in the set, X is not. And it's an upper bound. It's an upper bound for 2 reasons. One is because this thing, I upper bounded it by the absolute value of 2 things, the sum of 2 things. So I upper bounded the sum, used triangle inequality. And the second thing I get a 2 is because I have 1 for X in Y not and Y in X not. So it's 2. It's symmetry. And so this is X in F, Y not in F. I need a 1 over square root F squared coming from the normalization. And then I just have P X, Y. But what is this? This, if you think about it, you start uniformly in F, and you ask for the probability to not be in F.
The boundary.
This is exactly what we have as our measurement of the size of the boundary, as our boundary term in quotes, right? So there's 1 over F, sum over X in F, probability that in one, starting from X, that in one step, you're not in F. Okay? So this was an upper bound on the Laplacian of F. So now you see that we can define, if we take a Fellner set, a Fellner sequence, then we can, for each set in the Fellner sequence, define the corresponding n. We can normalize them to have norm 1. This condition was automatically satisfied because they're all finitely supported functions. Okay? And the only condition we need to verify is this. But this goes to 0, or its square goes to 0 because of the Fellner condition, because of the amenability. See, this is where we need to use amenability. Okay, so we constructed our sequence of functions that gave us, and let's write down the consequence of this theorem, this construction. So the consequence is that, again, you start with a Fellner sequence, you take the indicators, you normalize them, you apply the lemma, which is the truncated sum, or if you want to apply the green function, if you have a large enough dimension, and you get a sequence of almost harmonic cocycles, which are uniform Lipschitz, and then you use that to build the new representation with a cocycle that is harmonic. Okay, so theorem, what we proved is now theorem, if G is amenable, finitely generated amenable, and mu is first moment, then there exists a representation for a unitary action, that's right, unitary action. G on a separable Hilbert space H with, so I'm writing it this way on purpose to remind you that it's not a regular representation. Okay, some abstract unitary action in a separable Hilbert space with a mu harmonic cocycle C from G to H. Okay? this theorem, which was known since 1960s. We just gave an elementary proof. The usual approaches to this theorem would go via using property T or the absence of property T and spectral theorem or something like that. That would be the shortest way to go for it. But these are two. So property T is a very deep notion that I would need to spend a lot of time talking about. And the spectral theorem for general unitary operators is a deep theorem. It's not like a trivial theorem. You know, you have a continuous spectrum. You have to talk about when one is not in the spectrum, but when one is in the spectrum, but it's not an eigenvalue, and that's what you basically have here. But we did it like just got our hands dirty a bit, did some sums, did some things, right? And this is how we prove this cycle. So if you know deep mathematics, you can make the proof shorter. But if you want to be elementary, you cannot. And if you want to quantify things, you cannot use abstract theorems like the spectral theorem. You really have to get your hands dirty at the end.
For any Markov chain, one is in the spectrum, right?
Yeah, spectrum of what? We have to be careful where what P is acting, what P is an operator on. Is it in the spectrum of L2?
No. I don't know.
The constant functions are not in L2. Okay, you have to be careful.
But those two constructions use the same action.
What?
Those two approaches to constructions use the same base.
I don't know, because the other one is abstract. You have the spectral theorem, you project onto the things and you do some abstract nonsense and you get something which I have no idea what it is. In fact, I don't even know if it guarantees a separable Hilbert space in that case. This construction guarantees separable Hilbert space because I stayed in L2 the whole time. Just changed the representation. Okay. Let me give you one consequence. Okay, we won't do the rest. Okay, next time we'll start. Tomorrow we'll start talking about like how to go use this for Gromov's theorem. Okay, but two consequences of this thing. One consequence, corollary. If mu is in a finite first moment, then the dimension. Remember, we had Lipschitz harmonic functions G mu. Right, these are functions which are Lipschitz with respect to some generating set, some Cayley graph. Then it's any generating set, right? It's just a different Lipschitz constant, but any Lipschitz. So harmonic functions which are also Lipschitz, dimension is strictly greater than 1. It's always at least 1 because you have the constants. Constants are always there, but this is strictly greater than 1. And I want to remind you, when the entropy is 0, when the random walk entropy is 0, we already proved that there are no bounded harmonic functions, right? We showed that any bounded, we had the entropy inequality, the Cool inequality, which told us that if you have a bounded variance, right? Then, so if you're a bounded harmonic function, for example, then the function is constant. So it could be that the dimension of the bounded harmonic functions, and in fact, in the amenable case, that's kind of the typical thing, that the bounded harmonic functions have, or for sub-exponential growth, the entropy is always, the random walk entropy is always 0 because you cannot get enough entropy in a ball of radius t, right? So so the dimension of the bounded harmonic function is going to be 1, and to be trivial, okay? But the Lipschitz harmonic functions, no matter what group, is going to be bigger than 1, okay? So proof modulo one step that we didn't do yet, okay? Because we didn't talk about amenability and non-amenability and stuff like that, okay? But you're going to have to trust me. So let me write it maybe in a different color. What we didn't prove, okay? This is it. The theorem is true. There's always a non-trivial, non-constant, a Lipschitz harmonic function, at least one of them. Okay? So proof. If G is non-amenable, then the dimension of bounded harmonic functions, G mu, is strictly greater than 1. In fact, it's infinite. Okay, and of course, any bounded harmonic function is a Lipschitz harmonic
For,
function.
for any mu.
For mu in SAG1, yeah, it's true for any, yeah.
Then it's either one or infinity, right? Or
Yes, I want infinity. The fact that it's one or infinity is a bare category, and the Iran will tell you about. You just cannot have a what is it, a Banach space with a countable dimension. Right?
But we proved this using some B finite.
Yeah. We proved, right? Yeah, we proved it. Okay, so for you always have a non-constant bounded harmonic function if you're non-amenable. The proof is actually quite easy. I need two more steps. I need one to show you that the entropy is positive, the random walk entropy is not zero or non-amenable. And two, to show you that that implies. We didn't do both directions of the criteria, but they're easy things. And if we get enough time to talk about bounded harmonic functions, these are probably the first things we'll do. Okay, but I didn't discuss. It actually follows because the operator norm of P, the transition matrix, is strictly less than one if and only if the group is non-amenable. Okay, and this immediately gives you things about entropy, about it's like all the inequalities become like very, very quick. So all you need is the full entropy criteria, and but I'm going to skip this for now. For us, what's important is that there is always a thing. So when G is amenable, okay, then we have our harmonic cocycle. Right? Abstractly, we have some Hilbert space acting on it, unitary operators, and we have a harmonic cocycle with respect to this action, right? Sorry, with a what? Non-trivial. I mean, it's not the zero function, okay? That's very important, right? It's not the zero function, right? So, so C is non-trivial. What this means is that there exists an X in G, V in H, such that C X inner product V is not zero. You agree? Right? Because if C X is inner product V is zero for every V and every X, C is the zero function. Define H from G to C by H at the point Y. So this X was the special X. H at the point Y is the inner product C of Y with V.
It can be just C of X, and it.
V can be chosen to be C of X, yes. Okay, so you define H to be this inner product. Okay, and now we check the harmonicity of H, right? So H is non-constant, right? Because H of 1 is 0, and H of X was chosen, so it's not 0. So we have a point that's not 0 and another point which is 0, so it has to be non-constant, okay? Also, what happens when I sum over Y, mu of Y, H of, let's write ZY, right? If I do average of H, right? I need to get H of Z, okay? Oh, by the way, why is this sum uniformly convergent? I need H to be Lipschitz, right? So I didn't say that H is Lipschitz. So H of say, so for Lipschitz, it's enough to bound the difference on edges, right? On some generating set, but okay, so I take YS minus H of Y, right, in absolute value. What is this? This is the difference of these two things in absolute value, which is less than or equal to the norm of CYS minus CY times the norm of V.
We get a cocycle.
right? But this thing is a cocycle. This is just y acting on C of S. But y is a unitary action. So it's just C of S. There are finitely many S's that you need to check for this, okay? Okay, or if you want, C is a cocycle, so C of S is bounded by some kappa times the distance to the origin. Okay, so H is a Lipschitz function.
We assume the G is finally generated.
Yes, O is finitely generated in all what we talk about. Okay? It was important in many, many different things. Otherwise, I don't even know what Lipschitz means. Have a finite symmetric generators. Okay, and then so this thing, so sum y, h, z, y, mu y, h, z, y, the average around z, this first of all converges absolutely because I can bound this just by the magnitude of z, y, which is bounded by the magnitude of z plus the magnitude of y, and the average of the magnitudes of y is always bounded because of the first moment condition. The first moment condition is very important. Otherwise, this doesn't converge absolutely. I mean, I need a first moment for Lipschitz functions to even be able to be harmonic. Just talk about the sums. And once I have a Lipschitz function, any Lipschitz function, the sum converges absolutely. Okay, for first moment. And then I can check what the sum is. And the sum is what? It's the inner product of the sum. Because it converges absolutely, I can bring it inside. So it's the sum mu of y, c, z, y, b. But we know that C is harmonic, right? I mean, harmonicity at the origin, but it gives harmonicity everywhere for a cocycle. You could expand the cocycle equation and see this. Okay?
It's not the harmonicity at the origin, it's the harmonicity at
It's it, but I said that all these harmonic cocycles are actually harmonic maps. It's just that when we need to verify harmonicity, we check it only at the origin because when you expand the cocycle equation here, you get a C of Z plus something which is harmonicity around the origin, which is 0. So this gives me C of Z, B, but this was H of Z. This is the harmonic equation. Okay. So the projections of a harmonic map are harmonic. Okay? Projections of a harmonic map are harmonic. Because the projection is a linear function. That's all you need. Okay. That is one consequence. 4 minutes for the second consequence. Second corollary. If G is amenable, this is in fact true for non-amenable, I'm going to write, but it's much stronger for non-amenable. Okay? If G is amenable, mu is a first moment walk. Then, for any t, okay, then there exists a constant. If you maybe use C, it's an epsilon, such that for every t, if you look at the expected distance t to the origin squared, expected distance to the origin squared, okay? This is at least, so kind of the speed of your random walk is not less than square root t. On average, your random walk would go slower. This is, sorry, epsilon. This is tight because on ZD, for example, we can prove that the random walk goes to, remember the martingales we had for the random walks on ZD, right? We had a constant, we can get a constant epsilon where there's an equality in this thing. So this is tight inequality. For non-amenable, you can remove the square. In fact, you can get a much stronger statement. The lim inf of xt divided by t is positive. Probability 1. Okay, so you have positive, you have actual positive speed, but this is sometimes referred to as the rate of escape. So the rate of escape is at least square root t for any random walk on a group. Now this is not true for general graphs. It's not true for general, and in fact this was an open question until something around 2010 maybe, or something like that, or 2008, or. I mean, this, I remember when this was solved, so the person who gave this proof was Anna Erschler. But she never published it, and then it was published in a paper by, well, in the same paper, Liam Paris published it, but the argument was circulating. I mean, it's her argument. She noticed these harmonic cocycles give you this, so let's prove this. Proof, okay, so it's a theorem for any group, for any random walk, but just because non-amenable, you get positive speed, so it's much stronger, okay?
Is the proof harder for non-amenable?
No, it's easier. This was known. I mean, non-amenable, you have the exponential decay of the heat kernel, the fact that you have the operator norm of this transition matrix is strictly smaller than 1, gives you a lot of information. This is a very, very strong condition. Non-amenables things are usually easier to do, actually. Okay, so the trick was to do it for amenable, so let's prove it for amenable. So first of all, we take harmonic cocycle as usual. That's why I'm doing it now. So there's some unitary action with harmonic cocycle, right? Okay, and now we look at C of x. We know that there is some kappa, that this is less than or equal to the size of x. Oh, I didn't say what size, what is this absolute value of a group element here? That means I fixed some K graph, right? I mean, if I fix some K graph, if you change this K graph, it will change this constant, right? Because it will just have a different constant in front. So, okay, but we know that there exists a kappa such that for every x, this equation holds, right? You just take the kappa, which is the maximum over your generating set of the this is wrong, the norms of C of S, right? And then because of the cocycle property, you get triangle inequality gives you this. We did this already, right? Okay, one second, I'm almost done. Okay, so now we look at C of xt. Okay, I have to do t plus 1. Norm, squared, expectation. How can we compute this? Well, we can compute it by first conditioning on ft and taking expectation of that, right? But what is C of xt plus 1 conditioned on ft? It's averaging over some random walk element, right? Of the norm of what you had at time xt times this, right? This inner conditional expectation is just this number. Xt is now random. And you take the expectation of this whole thing. Okay, do you see it? Right? When I fix, if I know where I am at time t, then the next step I have to average over just taking a random step of the random walk, right? So this mu. Okay? This is the conditional expectation, and then you average that. But good, I have a cocycle. So this becomes C of xt plus xt acting on C of u. Right? Okay. Xt acting on C of u. Yeah, what did I want to do with this? Yeah, so now I need to open up the norm. Not the norm. This is a very nice property of squares. One property. We're going to use it again at some point. We have to be very conscious of what's going on. So let's see. So we can write this whole thing as the following. It's the expectation over xt and u, which are independent. And u has the law of x1 of u, of just one step. Okay, instead of writing the sum over the mu, right? This is the expectation of that. And then we write the following. We have this times itself, inner product with itself, right? So we have C of xt plus xt acting on C of U, inner product with C of xt plus xt acting on C of U. And all of this in expectation.
Replace little u with big U
Because I now,
we're going to do it
I'm
one
taking
here.
and now big U is a random element and I'm taking expectation over it. That's what the sum over U says here. Okay. Now let's see what this says, right? Inner products are easy to, again, this is the square. You know how to open up a plus b squared, right? That's what you know. That's what we're using here, okay? So this inner product becomes, I'm not doing the outside expectation. It becomes C of xt with itself, which is just the norm squared. It becomes xt acting on C of U with itself, right? Everything is inside the expectation. Everything is inside the expectation. And then I have 2 times the cross term, but once this way, once the other way. So it just becomes the real part, twice the real part of the thing. So it's twice the real part of C of xt with xt acting on C of U. All of this is inside the expectation. Okay? Now let's see what the different expectations are. First of all, what is this? This is, so this is expectation of the norm of C of xt squared. There was no inequalities. Everything is equalities up to now, okay? Plus expectation of C of U norm squared. This is a unitary guy, right? So I can throw him away. So I'm only left with the U. And C of U is the same as C of x1 when I take expectation. Same measure. So this is C of x1 norm squared.
Repeat that. Oh, xt.
xt acting on this thing disappeared, and then I can replace U with the x1 because it's the same measure, right? I wrote the U not to be confused with the x1 of the original random one, right? And then I have another term, but this expectation is 2 expectations of independent guys, right? So I can write it this way: expectation just over xt of 2 times the real part of cxt, and I bring in the expectation, I mean, it's linear, so I bring in the expectation of the U guy, okay? So it's this with the sum over U, mu of U, of C of U. But what is this? This is just 0, harmonicity, right? If you want, when you take the expectation of such an inner product, and you understand what expectations in Hilbert spaces are, right? Averages, then you're averaging this and averaging this because they're independent. Okay, but I wrote it out properly. There should also be an xt acting here, that's fine. Okay, but it's xt acting on the 0 vector, so everything here is 0. What did I get? You see the equation I get?
Just t times 9.
Yep, so if I get, so in conclusion, the expectation of C of xt squared, right? You can keep peeling them off one by one, and you just get t times the expectation of 1 step squared. There's your epsilon. Okay, there's your epsilon. How do we know that that's non-trivial? I mean, if it was 0, it would mean that C of x1 was almost surely 0. Because of harmonic cocycle, it will tell you that it cannot be 0. Okay, otherwise the cocycle will be trivial. Okay, one last thing. How do I get a lower bound on this? Well, this is just bounded by kappa squared times the expectation of xt squared, because we know what this is bounded by, right? So this divided by kappa squared will be the epsilon here, and we get the lower bound. Okay, so it's a very easy proof once you know harmonic cocycles. Harmonic cocycles, in this case, it replaced a homomorphism into an additive group. Right? It was a homomorphism with a twist, but we were able to get rid of the twist in the squares. Okay, this is something to notice. Good.
That was the proof.